predicted, their memory is unimportant. But individually you can't. In fact, that's still a problem in biology. Thermodynamics of systems with memory. We still don't have precise results as in classical thermodynamic circuits. The entropy of the universe, Flash said, can never decrease. I've lost control. This is Joule and Kelvin. Joule had a dogged persistence. I don't know if you know the story. Joule used to turn up in the Royal Society and make a presentation of equivalence of work and heat. So we'll calculate this. He calculated this 4.18 joules per calorie and so on. But he would come up with an experiment, and after a while the Royal Society was convinced. They said, enough, we are convinced. He said, I am not convinced. I'll show you one more experiment. And apparently there was a door in the back like here. And the Royal Society members, as soon as Joule came in here, they would all escape there. The only person who sat through all of Joule's lectures was Thomson. And the Kelvin, Lord Kelvin. And he sat through, he supported him. It was necessary because Joule was a commoner. And Lord Kelvin was part of the sophisticated society. And his support was very important. But it said finally Joule got married. And he went on honeymoon, and the Royal Society people were very happy. But one of the Royal Society members also went to honeymoon in the same place, and he discovered Joule was standing up at the top of a waterfall. His wife was at the bottom holding a thermometer. Joule was verifying that the loss of potential energy was equal to the increase in internal energy. It takes dedication. You see, the only thing Joule did, everybody knew that there are two ways in which a closed system can exchange energy with the surroundings. Joule said there are only two ways. He said it's either heat or work. If it's not heat, it's work. And work is always finally verified by showing equivalence to lifting of a weight. Because Newton had just discovered gravity, not just about 200 years earlier. But the idea of saying, just adding that word, only two ways, takes so much of effort. And you can't quite understand it because you take it for granted now. But if you go back and think about the time when Joule was doing these experiments, he was creating a path of scientific work, and he insisted that there are exactly two ways. And so then heat and work, he said, are equivalent. Meanwhile, Carnot was showing that they were asymmetric. You could go from one to the other, but converting the other way around, you had to make some sacrifices. So he said internal energy is a function of state. While there was a Q and a W which were both functions of path, he showed that the difference between these two was a function of state. So essentially the discovery of thermodynamics is the discovery of two functions of state. If you take PVT systems, other than PVT composition, they said there are also two more functions of state. One is the internal energy, and this other is entropy. If you grant me these, the rest of it is calculus. All the other derivations in thermodynamics follow from calculus. So really your teacher teaching you thermodynamics, he has to have you nodding for first two classes, and you can ask a lot of difficult questions. And the only way we handle those questions is to say, don't you know even this? Because some of these are elementary concepts. There's no way you can, you sort of assume everybody knows these elementary concepts, and then you proceed. But if you grant them that, then the rest of it is absolute logic. It's simply derivation after derivation. So the internal energy of the universe, he said, is a constant. And Lord Kelvin was a great supporter, but he was embarrassingly self-confident. He wrote the Cambridge Tripos. And he was absolutely sure he was going to be the first. So he sent his peon and said, go look up who is second on the list. And he came back and said, your lordship, sir. So Lord Kelvin was actually number 2. There was another person who got the thing. But he also provided tremendous support to Joule in the Royal Society. He's also famous for making a lot of wrong predictions. But he was a great scientist, and he provoked thought. He said nothing heavier than air can fly. But before he finished saying it, the Wright brothers were flying an aeroplane. So he had to eat his words. But on the other hand, he was a thinking individual, and he provoked a lot of thought. He certainly helped science a lot. In fact, as Carl Sagan says, it's the methods of science that are important, not the results of science. Because as new facts come in, you can use the same methods to deduce new conclusions which may be different from what you had before. So then Van der Waals and Van Laar, you must have seen those names. They plague you in all exams, I'm sure. Van der Waals was the first one to write down an equation of state that was so beautiful that it's still used. In fact, in theory, Van der Waals equation is one of the few equations of state that has no qualitative contradictions with the thermodynamics. In undergraduate classes, you don't know what a qualitative conflict would be. But if you went to graduate classes and did stability, it's very simple. When you do calculus, you say du is equal to 3ds minus pdv and so on. But you actually, when you write a differential, you have to write second derivatives, third derivatives and so on. So when you say something is a minimum, you have to verify that the second derivative is positive and so on. If you do that, you come up with what are called stability criteria that tell you that no gas can increase in pressure if the volume is increased. If the volume is increased, the pressure has to decrease. These are compulsory statements. You sort of take it for granted, but those proofs come from stability analysis. And he was the first one to produce an equation of state from just physical reasoning. And Van Laar was actually his student. And if you think profs are difficult now, you must go back and read about Van Laar and van der Waals. Van Laar never became a prof simply because van der Waals ensured that his own son became professor after him. I mean, Van Laar was a phenomenal guy, but he made sure, he felt that he was not showing him enough respect in those days. Enough respect could be in various forms. But in any case, and he was a Nobel laureate, and he was a great scientist. He really, the van der Waals school was well known at that time. He worked on capillarity, he produced the first idea of corresponding states. And Van Laar was a very socially awkward scientist. He had a remarkable theory of solutions. And that's in fact one of two models in classical thermodynamics for a theory of solutions. There's no other theory to date. I mean, you can twiddle Van Laar's theory. Van Laar had to, in his theory, he had to use the van der Waals equation of state because van der Waals had declared there is no other equation of state. And now people use very boldly other equations of state, now that van der Waals is no more. But then Boltzmann and Gibbs. Boltzmann was a very moody German. I don't know if you know, he actually committed suicide, and he is the one who discovered the formula for entropy in molecular in statistical mechanics. The first one to write down the formula for entropy. Essentially, all the interpretations of entropy being a measure of the number of states, microscopic states in which a system can exist, an isolated system can exist, came from Boltzmann. And the Gibbs was an American. And in those days, in the US, there weren't many scientists. You know, the US scientific structure was created by Hitler and Roosevelt. Hitler chased away all the good people from Europe, and Roosevelt welcomed them. And then, in a matter of 5 years, America became really the mecca of physics. But Gibbs sat and Gibbs actually, there are some stories. I can't find these stories in Google now, but when I was young, I read the stories somewhere and I'm not able to locate it. But the story goes that Gibbs actually, he was also a mathematician. So he first asked for a job as an engineer and they said no. So then he became a professor of mathematics. It doesn't work so easily these days. But secondly, he went to army and they rejected him. They said you can't join because his health was not too good. At the same time, I was told that he was jilted by his girlfriend. So he finally took to become a new professor of mathematics. I mean, I'm not suggesting professors of mathematics also, I won't go through this process. But he used to work alone, absolutely alone, and nobody knew of him in US. He was not famous. And they gave him a small room with a leaky roof in the 3rd floor in Yale University. And he worked all alone for 3 years before he produced this treatise on statistical mechanics. It's such a complete thing. It's 150 pages. And he had nobody to verify any of the intermediate results with. At the end of these 150 pages, he compared the specific heat of argon as he calculated it with the experimental value and didn't agree. So he writes in the end, our results must all be considered tentative because they do not agree with experiment. And 2 years later, when they measured the specific heat of argon accurately, they found Gibbs was right and the old experiments were wrong. I mean, it takes a tremendous brain to do this quietly for 3 years without any reassurance. I mean, you all know in the exam, if you have an intermediate step, hey, did you get 8.2? And then the fellow says quietly, you know, when the invigilator is looking the other way, he says, yes, I got 8.2. Then you're very reassured, you go ahead. And I mean, it's not just you as students, we all have done it as students, so don't do it. But you need reassurance from time to time. But Gibbs sat there for 3 years, he had no reassurance whatever. At the end of it, he wrote it down. Then actually a British physicist came to Yale University, he asked the president, I want to meet Gibbs. And he sent him to a professor in some other department. And he was very disappointed. He said, I came to meet the Gibbs. He said, oh, you mean that obscure fellow who sits up there in the attic? We don't think much of him. Then he went and met him and came back and said, look, Josiah Williard Gibbs is the only scientist you have in your entire university. Nobody else counts. Then they woke up to the fact, then they gave him a salary. For a long time, they didn't give him a salary also. Anyway, here's classical and statistical thermodynamics. Boltzmann introduced the kinetic theory. That S equal to K log omega is actually imprinted on his grave, on the tombstone of Boltzmann. It's a formula for calculating entropy in an isolated system, where omega is the number of states, microscopic states in which an isolated system can exist. Gibbs wrote 2 manuscripts. One was on equilibrium of heterogeneous substances. It's a beautifully written document, and he derived a lot of vector calculus in order to do this, surprisingly. And elementary principles of statistical mechanics. That's the one I was telling you about. After 150 pages, you draw a conclusion that you compare with experiment. Then, what are the 2 laws? Let me go back and tell you the 2 laws. You know this, but I'm just summarizing it so as to give you a perspective, hopefully. First is that the energy of an isolated system is a constant, and the entropy of an isolated system is ever increasing. One of the principles that Gibbs used when he did statistical mechanics is, he said he's going to make assumptions about an isolated system. These can't be tested, because the minute you do a testing on an isolated system, you spoiled its isolation. It's no longer an isolated system. But on the other hand, you have to relate the experiment at some time. So making assumptions about an isolated system, you have to draw conclusions about a closed system and an open system, and then compare with experiment. And so far, there's been no contradiction with experiment. I mean, no contradiction to theory. So if you find a contradiction, you're pretty much in for a Nobel Prize. So watch out for contradictions that may arise, but don't rush to conclusions, because even the patent office will reject. I don't know if you know how the patent office works. The second law is so well established. If you go to the patent office and file a patent for a heat engine, he will look at the maximum temperature and the minimum temperature, read his table and say how much energy you will produce. If you produce more, he'll say take it back. Can't be done. And the patent office clerk is not a thermodynamicist, but he has this table. There's so much faith in that table. So the second law is so well established now. But the equivalent statement of the law is simply that the internal energy and the entropy are functions of state. And there are only 2 kinds of applications that chemical engineers are interested in. One is criteria of equilibrium. When has a system come to equilibrium? And extrema in work. The first one is important because you can't keep pushing a reactor beyond a point. I mean, if it reaches equilibrium, there's no point in your saying I'll fiddle, I'll see if I can get better conversions. You can't change the calculus and get a different equilibrium. So that's now accepted. And the other is extrema in work. What's the maximum work I can extract out of a system? Or what's the minimum work I can get away with to create a change of state? These are interesting questions. And these are results that you've all seen. I'm sort of summarizing them. So you have the law that says du is less than or equal to T ds plus delta W. And if you have an isentropic process, S is constant, ds is 0. So delta W is greater than or equal to du. And delta W with a plus sign means work done on the system. So the minimum value has to be equal to delta U. So if you want to create a change of state, the minimum work you have to do on a system is actually the change in the internal energy. And then if you add dPs, d of Ts to both sides, if you subtract d of Ts from both sides, you get an equation in terms of free energy, Helmholtz free energy, which is A, and you get the result that W minimum in an isothermal process is delta A. That's of great interest to chemists, particularly because they do work with closed systems in the laboratory. And engineers often work with open systems, so I'll discuss that in a minute, where temperature and pressure are the ones that are held constant. If you go back to PVT systems, delta W is simply minus PdV, so you have an equilibrium criteria that says the internal energy is a constant at constant S and V. Then depending on the variables you hold constant, if S and P are constant, enthalpy has to be a constant. Enthalpy is simply an additional variable introduced, and you realize that you started with 5. If you're talking about pure component system, you have P, V, T, U and S, only 5. And you add a free energy, Helmholtz free energy, a Gibbs free energy and an enthalpy. So you have 8. And we have 8C, 5 ways of choosing any 5 variables. And that's why thermodynamics gets so confusing. In fact, Van Ness, who's a great thermodynamicist who's in RPI, he used to have a board outside his lab apparently. I haven't seen it, but I've heard from my friends. The board said, blessed are they who go round in circles, for they shall qualify as thermodynamicists. Because you start deriving thermodynamics, you come round and round, you can come back to the original equations. So the rule when we teach thermodynamics is to say stop going round and round as soon as you get measurable quantities on the right hand side. So if you are trying to calculate change in a property, you do that. but there are each C5 games that you can play, and out of this 5 you have these equations that relate each of them, so you can get Maxwell relations between any of these, any subsets of these quantities. But let me come back here. Equilibrium says A should be a minimum at constant T and B. Then if you're looking at open systems at steady state, you rewrite the equation, because out of the work done, there is flow work that has to be done for pushing material into the system and taking it out of the system. So you take that out separately and ask what's the shaft work or what's the useful work that you can do. And that's delta Ws. And you put it into those equations and ask what happens in a steady adiabatic process. And you get the rate at which the work is done per unit mass flowing through the system is in fact equal to delta H in an isentropic process and delta G in an isothermal process. That's why delta G is so important for chemical engineers, because you're often dealing with steady processes at constant T and P. You might say the temperature changes everywhere. That's where thermodynamics comes in. You draw an envelope around the whole plant. The raw materials go in at room temperature, the products come out at room temperature and pressure. The rest in between, I'm indifferent. You can say it goes to 1000 degrees, it comes back to minus 50 degrees. It doesn't make any difference to me. My envelope, my system is now the whole of the chemical plant. So I can simply go to Madras refineries in Chennai Petroleum and tell them this is the amount of work you should have done. Their actual work is much more, so they get very angry with me because they're order of magnitude away. But that's reality. But the point is you can improve it to that point. That's thermodynamics sets a limit. And delta G is very important. So a chemical plant where raw materials and products leave at ambient temperature and raw materials enter, it doesn't matter what happens inside. In fact, in thermodynamics, the thumb rule when you model a thermodynamic system is to draw an envelope on as large a system as you can. Of course, you lose some information. You can't say anything about what happens inside. But if you can, as far as possible, draw an envelope that includes everything that you don't worry about. Details, internal details you don't worry about. So it's also valid for systems with negligible holdup. I'll give you an example. For example, take a pump. This device is used, it doesn't look anything like this. As I said, thermodynamic people have the liberty of drawing circles and saying this is a pump, this is this, and so on. But if you are doing repairs under the hull of a ship, then you need a power device. And you carry 2 tanks. You have compressed air in one tank and it flows to the other tank, because if you let it out, the pressure there, 10 meters below the surface, it's 10 atmospheres, so you can't let it out into the thing. So you have another tank into which you let it out and work is done during the expansion. You can calculate what's the maximum work. In this case, I've done a calculation just to give you an example. You can calculate delta A. Again, you have to choose systems very cleverly. You choose both tanks together as the system. Then the N1 moles that was in tank 1 has expanded to the final state, N2 moles in tank 2 has compressed to the final state, and you can calculate the change in Helmholtz free energy. So one is minus, the other is plus. So you have net energy of 46.9 kilojoules. It's a very interesting calculation, because without going into details, no matter what your pump is, you can come up with any invention of your own, you cannot get more work than this. And let me talk about the Gibbs free energy. I've told you that the Gibbs free energy is very important. You have to calculate the Gibbs free energy as a function of temperature, pressure, and composition. And essentially, G is a function of T, P, and composition. So I can go to calculus, because G is a property of state. dG is simply expanded in terms of first order differentials. You get this minus STP plus VdP plus mu I dNi. Mu I is defined by this equation. It's actually the derivative of G with respect to Ni, holding other variables constant. It's called Gi bar. It was in fact a remarkable thing that Gibbs did. He said, I'm going to integrate this equation. And thermodynamics is one subject in which you can integrate an equation, put in some physical inputs, and then differentiate it, you get a different result. You don't come back to the original state. It's remarkable. In this case, for example, Gibbs suggested that mu I is an intensive variable. That is, it depends only on temperature, pressure, and mole fractions. It doesn't depend upon the extent of the system. The number of moles don't make a difference. If that is true, I can go from an initial state of n moles to k times n moles. Then between those two states, these are all thought experiments, you can just integrate between those two states and you get G is equal to minus ST plus VP plus mu I Ni. So you get G is equal to Ni mu I at constant temperature. So I can just integrate that. If I do it at constant T and P, SDT, VDP will vanish. Then G is simply Ni mu I. These quantities Gi bar are called partial molar quantities. It's been given a symbol mu I because it occurs again and again and again in thermodynamics. So then if you differentiate Ni mu I, you get the Gibbs-Duhem equation. That's the most important equation. It's actually equivalent of saying the sum of mole fractions is equal to 1. If you had a description in terms of mole fractions, you will simply say the sum of mole fractions is equal to 1. If you have it in terms of chemical potentials, one of them is not independent and they are governed by this Gibbs-Duhem equation. This is important because you must pause and think that your life depended on calculating delta G. Then you will know the value of these steps. Because otherwise you can say, oh, this is too complicated, or how is it related to what I am doing and so on. But if you think your life depended on it and you are intelligent enough like Gibbs, then you can put it together and derive results. Let me go back here. So d mu I is simply, mu I is the chemical potential. It's a function of P and P and composition, mole fractions. So I can write that. And again, I can go back and compare it with the Gibbs-Duhem equation, substitute it to the Gibbs-Duhem equation. The final form of the Gibbs-Duhem equation I get is xi delta mu I by delta xj is equal to 0. This is a set of r minus 1 equations in an r component system, but there are r variables. So there is 1 degree of freedom, and that's where modeling comes in, that's where the theory of solutions comes in, where you can guess one chemical potential. Any of you can guess any model for the chemical potential. The rest of the chemical potentials are determined. So if you are Akhilesh, you can say this is Akhilesh model for chemical potential, and nobody can say no. But if it doesn't, if out of that model you don't have any comparison with experiment that agrees well, nobody will bother. Your model will be forgotten in a couple of years or so. So there are many models that have been proposed, but very few have survived. And basically, they are all solutions to the Gibbs-Duhem equation. These solutions to xi delta mu I by delta xj. By inspection, you can see that mu I was proportional to log xi. That equation will be satisfied, because you will get one term for I, xi delta log xi by delta xj. When j is equal to I, you will get one term, 1. And then when j is equal to r, the last component, you will get minus 1. So you satisfy that equation. And that solution is called the ideal solution. You can show, then it follows that this chemical potential model corresponds to what you know of an ideal solution, namely non-interacting particles, no change in enthalpy, no change in volume on mixing. That's our concept of an ideal mix. So this is the simplest solution. Go back, what we do is, societal behavior also influences scientists. So if you're guessing chemical potential, then the rebellious question is, why should I guess mu1, why can't I guess mu2, and so on. So there's no arbitrary way of choosing one. So in order to make peace, you choose a common quantity that you model, and the common quantity is called Gxs. Gxs is the excess over the ideal behavior, and this is important for engineers. We always have a limit in which we have a default option, because engineers don't have the choice of saying I don't understand the system. You have to design it anyway. So you need a default option. At first you would say I assume it's an ideal system and I make the design. So instead of, you have a Gxs, and you can always put Gxs equal to 0 if you don't know anything about the system. But essentially we model Gxs, and the way you do it is simply because, for example, if you have a binary system, delta G ideal is RT x1 log x1 plus x1, x2 log x2, and Gxs, if I know Gxs, then I can solve the Gibbs-Duhem equation. And essentially mu1 is simply given by this. You can verify this, it's simply algebra. So instead of modeling any one chemical potential, you model the sum of the chemical potentials multiplied by xi, excess over the ideal behavior. Then you can get these things, and all you have to do is guess Ge. And then Van Laar came up with a beautiful model. It's one of the best models. I can't imagine somebody in 1890 coming up with a model like this. And you should read the literature at that time. There were two people, Van Laar and Dolzalek. Van Laar developed what you would normally describe as the physical theory of solutions. That is where solutions are non-ideal because of interacting forces, and you evaluate the non-ideality. Dolzalek said you're all very foolish, all systems are ideal, except you're not looking at the right species. If you add A and B, mix them, they are not A and B in solution, they may be A, B and B. As a mixture of A, B and B, it's ideal. But you're looking at A and B and you're saying it's non-ideal. In fact, you must read the literature. We scientists today are much more polite. We don't call names of, call other authors by names. But these people say there are idiotic people who think solutions are non-ideal. And this fellow writes, there are other idiots who think all solutions are ideal. It's very explicit. I mean, they were just very frank, that's all. I think nowadays people are very sophisticated. They think things but don't write them. But anyway, so these are the models, and essentially, I think I will not go into this. If I have time, I'll talk a little bit about, I'll tell you about Van Laar's model. It's a beautiful model. You might say, what's the big deal? What does it matter if something is a function of state? Van Laar said, we understand mixing of ideal gases. So that's because it's an ideal mixture. I have this x1 log x1 plus x2 log x2 for a binary mixture. I know how it mixes. But I have to get the ideal gas state. Now I'm mixing two liquids. That's what I want to understand. If I mix liquids 1 and 2 and produce a mixture, that step I don't know how to calculate delta G for that step. So what he said was, every component I will reduce at constant temperature, I will reduce the pressure to 0, then it will evaporate. So I can get ideal gases at pressure equal to 0, everything is ideal, I mix them, and then I condense them. For the evaporation and the condensation, if you go back to Van der Waals equation, you can calculate the energy change, du you can calculate. And he calculated du and showed, and said delta U is the same as delta G because delta V is negligible, and he said entropy, excess entropy is 0. Even today, our delta G of mixing has two components, delta H of mixing minus T delta S of mixing. All the theories either assume delta S of mixing is the same as the ideal mixing and calculate delta H alone, or they assume delta H is 0, the thermal solutions, and model delta S. So Florey-Huggins, for example, said if you have large polymeric molecules, the major change that happens would be entropic because the rearrangement of the molecules would have to be done, and his theory calculates the delta S. So all these theories to date are like this. And Dolzalek simply wrote a chemical reaction equilibrium between two species to find the hypothetical species and then use the ideal model. Both models work. Dolzalek's model used even today where there is evidence of such association. If you don't have evidence, you don't use Dolzalek. The other important criteria is bounds on work. Can you calculate bounds on work? He said this is a summary. If you have a closed system, then your isentropic work is either plus or minus delta U. If you're doing work on the system, the minimum work is delta U. If you're getting work out of the system, it's minus delta U and so on. So I have these 4 cases, and of particular interest to us is delta G. As I said, delta G is delta H minus T delta H. Yes. And delta G makes ideal is something that we know. So if we don't know anything, we have a default option to fall back on. And you need to worry about the numbers. It's just a distillation column with an example where you are separating ethyl benzene for paraxylene, M-xylene and orthoxylene and so on. You get the composition of all of these and you ask what is the work of separation. Since the work of separation in an isothermal flow process is delta G, I take delta G of each of these and subtract them. And I take the product minus delta G of the feed. You will get delta G. Delta G ideal turns out to be 2.86. Then you have various models. I've used what's called the regular solution model. This was done by Hildebrand. It's actually very similar to the Van Laar model. And you get G excess is minus, so the actual delta G is 0.98 kilojoules per mole. That's the minimum work you have to do to actually separate these components. So the distillation column, the whole unit, you can say what the minimum work that needs to be done is. So if it is much more than 0.98, then you know there's scope for improvement. You can ask, how can I improve this process? If it's very close to 0.98, there's no point doing it. So the enthalpy contribution in this case is 80%. Now, work per mole, this leads you to a concept of work per mole. If delta G is RT x1 log gamma 1 x1 plus x1 log x2 log gamma 2 x2,